So today I'm going to show you another use of randomness in machine learning, and this is an extremely powerful use of randomness. So the specific result I'm going to talk about is something called follow the.
Your document camera is not on, I think.
My document camera is not on, of course. Just a second. So I'm going to talk about a result or an algorithm called Follow-The-Perturbed-Leader, FTPL, or sometimes known as FPL. But let me tell you sort of what the basic idea, and this is really a powerful use of randomization. And it's actually a very contemporary use in the sense that there are lots of recent results which are doing more and more of this, especially developed over the past decade or so, is to essentially one can think of it as how to prevent overfitting in ML. And this has lots of connections to doing what is called robust machine learning, and has deep connections to a notion called differential privacy. So what I'm going to tell you today is really a specific result called Follow-The-Perturbed-Leader. It's another algorithm for the expert's problem, but actually it has connections to all these issues, and these are sort of very contemporary research topics, and indeed it is very closely connected to differential privacy. And a lot of the mathematics behind it. So let's go back to the expert's problem. And if you remember, the setting is we have n experts making predictions every day. So you have a collection of experts and they're all making predictions every day, and every expert incurs a loss every day. The algorithm picks an expert, or technically a distribution of experts, and incurs that loss, or that expected loss. And the aim is to be competitive with the best expert in hindsight. So let me make things a little formal here. So at time t, right, and this is going to be the time horizon, sort of how many steps or how many rounds there are in this process. So at time t, there is a loss function L of t, which takes an expert and let's say gives a loss whose value is in 0, 1. Just zoom out a little bit so that I have more space to write. And what we have is the loss of expert I is LT of I, and I can say the total loss is simply the sum over t. So this is the loss. And sort of we can define the optimum loss to be the min over all I of this quantity. That is the optimal loss. And also I can define IT star to be argmin of I sort of capital T star of t going from 1 to t of LT of I. So this is the optimal loss. And this is called the best expert in hindsight. And what we want is that the loss of the algorithm, whatever algorithm we're playing, should be at most, there are multiple ways of phrasing this. One way of phrasing this is equal to opt plus sort of the extra. And this extra is often called as the regret. And what you typically want is regret should be minimized. Typically, a regret which is little o of t is called sublinear regret. Now, we discussed an algorithm for this problem, which was the randomized weighted majority. And we showed that the expected loss of randomized weighted majority was, you could basically set a parameter eta and you would get something like O of log n divided by eta. Right? And by setting this learning rate, if the learning rate was set to be essentially root log n divided by t, then the regret was essentially O of root t log n. Right? And this is I should say that the randomized weighted majority also works in the case where the adversary, the one who's generating the loss function, is an adaptive adversary. The adversary can actually look at what the algorithm is doing, but cannot look at the randomness of the algorithm. So the randomness is private, but the adversary can generate his choices based on whatever the algorithm is doing. So this is a very powerful guarantee. Any questions about the setup? Because I'm going to dive into another algorithm for the experts problem called Follow-The-Perturbed-Leader. So any questions about that?
Oh, Professor, sorry, you might have gone over this. Could you give us intuition of the regret?
Sure. So one way of okay, so maybe let's think of it as you have the loss of the algorithm. And you're trying to compare the loss of the algorithm to something. So what we need is a benchmark. Now, an impossible benchmark to achieve would be the minimum possible loss. Because let's say that you knew what the loss function was. Then obviously the algorithm would simply choose the best expert for each round. And that just seems like it's impossible for any algorithm to be able to do that without knowledge. What I mean is, in every round, the algorithm picks an expert and then gets the loss. Now suppose you want to say, what is the minimum possible loss that can be achieved? Well, suppose the algorithm, consider this sort of super powerful algorithm that actually knew what the loss function was in every round. Then it would simply go and just pick the best expert for each round specifically. But that's just impossible to get. So instead, we construct a benchmark, which is the best expert in hindsight. So what this says is something like, if you looked at all the loss functions And you could go back in time and just choose one expert to stick with. Who's the one that you would stick to? And so the difference between the loss of the algorithm minus this benchmark, this is called regret. So regret is actually defined to be the loss of the algorithm minus this benchmark. And sublinear regret means that essentially, in some sense, you can think of as t goes to infinity, the loss of the algorithm actually approaches the benchmark. And this is like the rate of convergence. So does that give more intuition?
Yeah, thanks.
Okay, any other questions? Okay, now let me give you, now the randomized weighted majority is a very non-trivial algorithm. Like, I mean, in sort of, again, in hindsight, you can think that, okay, maybe it makes sense, you decrease the weights, but it was really a tricky algorithm to analyze and come up with. Let me discuss an algorithm which is seemingly much more natural, and let me call that algorithm FTL, or follow the leader. So what does follow the leader do? Follow the leader says, so at time t, the algorithm has seen L1, L2 up to LT minus 1. Right? It's seen all the losses so far and needs to pick a decision. So the algorithm could pick the leader among what has been seen. So now let me define I star of little t minus 1 to be the argument over I of the summation. Okay, now let's be careful here. So I'm going to say that S is going from 1 to t minus 1. So this is what has been seen so far. So this is the best expert amongst what has been seen so far. So the leader is the best expert. So this is kind of saying, like, this is what regret is trying to do. It's trying to be competitive with the best expert in hindsight. So at every round, the algorithm could pick the best expert in hindsight and play that. And so the FTL algorithm is simply at time t, choose or play the expert I star t minus 1. That's what it is. Does the algorithm make sense? This is called follow the leader. Very natural algorithm. Now, can you say something about the regret of this algorithm based on what we did last time?
Well, there's no.
Sorry, go ahead.
It's like at the end, you're definitely going to be following the best expert.
But only for that one round.
But only for that one round.
Actually, not even then, right? Because for the very last decision, you're going to follow the best expert amongst everything but that last one.
Yeah, but that expert has to be like almost as good as the best one.
That's right.
At that point.
Okay, so let me ask you a different question. Is this a deterministic or randomized algorithm?
Deterministic.
And we proved that deterministic algorithms cannot achieve sublinear regret. Right? Or we went through this argument.
Yeah.
Indeed, FTL can be a bad algorithm, and it's almost like, so let me show you a simple example. Why is FTL bad? Well, let's consider the following. Let's just say there are two experts. So it's really simple. Two experts. The losses, so initially, it's going to be 2/3, 1/3. Okay, this is the loss of expert 1, the loss of expert 2. Okay, and then I'm just going to switch. So on and so forth. Okay, let's look at what the algorithm does. So initially the algorithm, let's say picks arbitrarily. It doesn't matter. At this point, the algorithm is going to play expert 2. So the algorithm says, I'm going to choose the expert to be 2. And it's going to get a loss of 1. And the loss is 1. Now at this point, note that the first expert has a loss of 2/3. This is the total loss of the first expert. And the second expert has a loss of 4/3. So it says, oh, FTL is going to say, this is the leader, so I'm going to set I is equal to, I is in, do you see what I mean? I is the expert that's being played. Or maybe let me even be more formal here. So I'll say I1 star is equal to 2. That's it. At this point, I2 star is equal to 1. Then it's going to have a loss of 1. Now once it goes here, it's going to say I3 star is actually 2. And then it's going to suffer the loss. So on and so forth. The total loss is essentially going to be at least t minus some theta of 1. And then there's a theta of 1 because, because of that initial thing, just to set things up. But in every round, the algorithm loses. The best expert, or sort of the opt, which is the loss of the best expert, is at most t over 2, plus some theta of 1. So it's linear regret. Does this make sense? Does construction make sense? So you see that the losses just keep switching back and forth, and the expert has a lag of 1. The algorithm has a lag of 1 because the algorithm cannot look ahead. So the algorithm looks at the past, and it's sort of set up in such a way that the next decision is exactly the opposite of what should be done.
I have a question.
Yes.
If I may. Intuitively, it just seems like this is very unnatural, and like in most natural settings, this algorithm would lead to good regret. Is that correct? Is there any reason why that's wrong?
One can argue that if the losses were stochastic as opposed to adversarial, then FTL would perform well. But actually, a lot of contemporary movements in machine learning are going towards things like adversarial machine learning, where maybe someone is trying to fool your algorithm, and it is stochasticity is always an assumption. When you assume that the world is stochastic, that's like an assumption. It's a model on the world. Having an algorithm that can deal with adversarial inputs is always superior if you can get similar bounds. You're right that while this seems unnatural, it isn't implausible that maybe you're in a situation where your loss functions have some periodicity, and if you do follow the leader, you might just be lagging in the periodicity. Does that make sense?
Yeah. But even the weighted majority, I feel like it wouldn't perform well with this kind of setting either.
Weighted majority will give you t over 2 plus root t.
Right. It would be worse anyway. But
No, what do you mean by worse? It would be t over 2 plus root t. So it's going to give you root t regret. This is going to give you a regret which is weighted majority is basically going to give you the best expert plus some small noise.
Oh, okay. Sorry about that.
Yeah.
But it feel like with weighted majority, we would reduce the weights of both every round because we're flipping between right and wrong.
But the power of randomization is that you will essentially then pick each expert with roughly the same probability.
Oh, okay, I see. So then, okay, it would be better then, yeah.
So weighted majority is actually going to win. Because weighted majority is going to by the randomization, basically half the time it's going to pick the right law. It's going to pick, because essentially, okay, it's a good point. What is weighted majority going to do? Weighted majority, at some point you can imagine the distribution, it's just going to be half-half. And so essentially in every round there's a probability half of having a loss of 0. So weighted majority will have a significantly smaller loss. Questions?
Thank you.
Sorry, my question is why we choose 2 experts to such that we have 2 different loss functions.
I'm sorry, say that again? I missed it.
Why do we choose 2 experts such that we have 2 loss?
I'm giving you a bad example. So I'm showing you why is follow the leader bad, and saying that even when there are only 2 experts, follow the leader can really be bad.
Okay.
Right? So I'm giving a lower bound, a counterexample. So as I specifically say, when there are, even with just 2 experts, follow the leader can perform really poorly.
Okay. But sorry, another question is that naturally people will think that if we only have 1 loss, that will behave better, right? But why?
No, but the whole point of, in machine learning is that if there was only 1 loss function, then essentially the past completely predicts the future.
Okay.
The whole point is, even when the loss functions are changing, can you still do something that is useful?
Okay, gotcha.
And so the point is here, the loss functions are switching. FTL does poorly, but randomized weighted majority is going to do well. I mean, indeed, we showed randomized weighted majority does well even with adaptive adversaries, as long as the adversary cannot see the randomness of the algorithm.
Well, there's like one underlying loss function, and then the experts are predicting different things and incurring different.
That's one way of looking at it. So you can transfer that however you want, but you're right. You can think of it as just one underlying loss function, and one just transfers that into what decisions the experts are making. Like, is it going to rain or not? So there's one expert who's sort of getting it wrong on the even days, and the other expert is getting it wrong on the odd days. And what randomized weighted majority does, it kind of figures that out and says that, well, at that point you should be picking between the experts randomly. What follow the leader does is it actually has a very fundamental problem in machine learning, which is overfitting to the past. Right? That's what it's doing, right? Because it overfits to the past, even though the difference between the 2 experts is so small. Follow the leader is going to choose the one that is slightly better, who has slightly smaller loss. And indeed, like, this discussion will start telling us how we're going to fix follow the leader.
Okay, thank you.
Okay, so any questions? Again, it is important to note that follow the leader as is does work in certain settings. When losses are stochastic, it works. But there is this problem that it has, that it sort of overfits to the past. On the other hand, the algorithm is so natural that we would like to have some version of this algorithm. And so, as I said, the problem is that FTL was overfitting, and it turns out that in a beautiful result, so Kalai and Vempala, so this is usually attributed mostly to Kalai and Vempala, but Hanan in 65 had similar ideas, whereas Kalai and Vempala, who really brought it out, gave a nice proof and showed the applicability to a lot of machine learning. And this was called Follow-The-Perturbed-Leader, FTPL. What they basically said was just add some noise, add some random noise, and FTL works. So this is a remarkable idea. It just says add a perturbation and then just run FTL as is. And I'll tell you exactly how we'll do the perturbation. So there are different presentations. I'm going to present a version which some people call also, they call it follow the regularized leader. So this is it's called follow the regularized leader. It's, there are different ways of looking at it. I just put this out there because there are some notes that call it this way. But I will do a presentation of this, follow the regularized leader, although some people define it as follow the perturbed leader as well. This is different from Kalai and Vempala's version. It's weaker than Kalai and Vempala's version. Okay, so the idea is you have these loss functions L1, L2, up to LT, so on and so forth. We're going to add a loss function called L0, and this is going to be a random loss function. So we're going to add a random loss function at the very beginning. And then we're going to do FTL, for just follow the leader on that sequence. So let me define this formally. So recall that I define IT star as the argmin of the summation of Fs of I. S goes from 1 to t. Okay, so I want to define 4 quantities. So there's IT star, there's IT minus 1 star. So this is what FTL plays. FTL is playing this quantity. Now I'm going to define something called JT star, which is the argmin over I of S going from 0 to t. That's the difference. So I'm also incurring the loss from the random loss function. Sorry, L. I'm sorry, it's exactly the same, LS of I. Now, just to be clear, I'll say all losses are in 0, 1, except for L0. So L0 is going to behave somewhat differently. We will come to what it's going to do later on. We'll come to that later on. So JT star has this behavior. What follow the perturbed leader does is play JT minus 1 star. Right? So at time t, you've seen everything up to t minus 1. Follow the leader optimizes on all of L1 to LT minus 1. Follow the perturbed leader is going to add a perturbation to optimize. So we know that this algorithm is bad. So let's sort of get rid of it. And what we're going to do is follow the perturbed leader. Okay, so any questions about this notation? This notation is important. Hopefully you see the difference between the i's and the j's. So there's a difference between I and j and the index t and t minus 1. These indices are really important. Any questions about this?
On the left side, is that an F or an L?
I'm sorry, which that should be an L, I'm sorry. It's
L,
just the loss function. I shouldn't have written F. That was an error. So to analyze FTPL, we introduce sort of these, what I'll call a thought experiment, algorithms. So these algorithms cannot be implemented, but they will help us perform the analysis. And indeed, I wrote all of these to tell you exactly what's going on. So let me define this algorithm as BTL, which is called Be the Leader. So FTL plays I star t minus 1 at round t. BTL is it actually is going to play I star t. So BTL actually requires knowledge of the tth loss function before it plays. So you cannot implement this algorithm, but nonetheless it's a well-defined algorithm. And it's not obvious that BTL is going to do well. Because remember, BTL is not playing the best in hindsight it's not going to pick the best in hindsight and play that in all rounds. At every round, it chooses a different best, right? It keeps switching its expert, but it's switching based on the current loss function as well. And this is called Be the Leader. Now, analogous to the fact that you have FTL and FTPL, like this FTPL is a perturbed version of FTL, we can define a perturbed version of BTL, and this is called Be the Perturbed-Leader. That's another algorithm. So you have these three algorithms. This is the one that we want to look at. Now the reason to define these is we're going to say that, so it's going to, the algorithm goes in these steps. It says, let's look at opt. And we'll kind of say that Be the Leader is going to be at most opt. So this is going to be a simple argument. Then we argue that BTPL is kind of going to be less than this, but this is there's going to be some noise here. And BTPL is going to be similar to FTPL, but there's going to be some noise here. This is going to be exact, but here there's going to be noise. And then a trade-off between the noises is going to give us the full result. Okay, so is this, does the schema sort of make sense? There are lots of indices to keep track of, so please ask me questions if this is not making sense. You need to understand what all of these three algorithms are doing. Any questions? Also, I haven't told you how I'm going to generate L0. This is going to be very important for the analysis. How am I going to generate that loss function? Now, typically what happens is they will describe some closed form loss function and analyze that. I'm not going to do that, because what I want to show you is why did they come up with that particular distribution for the perturbation. And it turns out that there are very specific properties they were looking for, and they chose a distribution that matched those properties. And so I'm going to sort of keep that under wraps and show you in the end. What I want to do is just sort of analyze this and see what we need from the perturbation to make everything work. Okay, so any questions? So let me start with the easiest argument. And this lemma, which is basically just saying that BTL beats opt. Okay, so this just says that if you look at the summation of t going from 1 to t of LT JT star, this is what Be the Leader is doing. This is at most opt. Okay? And another way of writing this, which is going to be more convenient, is that for all experts I, summation of t going from 1 to t of LT of JT star is at most t of LT of I. Right? This is just saying that BTL is going to beat every expert in hindsight. So the proof is by induction. So let's prove by induction on little t that the summation of S, so any intermediate step, LT of JT star, so I'll just say for all I, is at most summation of t going from 1, S going from 1 to t of LT of I. Okay?
Professor?
Yes?
You say BTL beats op, but then you have the J star T index inside, right on the right side.
There?
Shouldn't it be I?
Are you talking about this one? Or this one?
Because we assume BTL was was the I star T. The above one, the one right above.
Good point. So my apologies. Right. No, you're right. I'm sorry. It should be I. Yes. Thank you. It should be IT star. Yes. It's a mistake. Right?
You want to write IS star, right? LS IS star.
Which one?
So I mean in the current line.
Oh,
it
that
should
one.
be
Yeah. Sorry, I'm mixing up my indices. My apologies. LS IS star is at most S going from 1 to T of LS of I. Yes, thank you. Okay, so this is what I want to show by induction. Okay? So let's just do, so the base case is just t is equal to 1. So what we need to argue is that for all I, L1 of I1 star is at most L1 of I, but that's the definition. That's the definition of I1 star. So this is true. So done. Now let's do the induction. So go from S1 to T of LS of IS star. Okay. Now we can break this up as 1 to T minus 1 of LS of IS star plus the last one. L of T of IT star, right? I just broke up the sum. Okay, and so now here's the thing. By induction, this quantity is at most the sum. This is going to be better than any expert, and so specifically it's going to be better than IT star, who's the best expert after T steps. And therefore, if I plug this bound in here, what I get is this is at most S is going from 1 to T of LS of IT star, who's just the best expert at the very end. But then, by definition, this is better than all experts. This is the definition of IT star. Okay, and that's the end of the proof. So it's some sort of a little bit of clever manipulations and application of induction. So this is simply saying that look at what be the leader does in t steps. Well, be the leader is also be the leader in t minus 1 steps, plus in the very last step it actually played the best in hindsight. So you know that because it was be the leader by induction was good on the first t minus 1 steps, in the first t minus 1 steps it was at least, or it was, the loss is at most the loss of IT star, which means that it's comparable with IT star, and IT star is the best expert in hindsight, so we're done. Okay, so any questions about that? Okay, so what we have right now is we've shown that BTL is less than opt. This is done. Now in our chain I have be the perturbed leader and follow the perturbed leader. Okay, so we have these two steps that need to be done. I'm going to focus well, actually, okay, let's actually do this part now. So we have be the leader, which we know is good. Now let's look at be the perturbed leader and see how we can compare that. Naturally, this is where some aspect of the perturbation is going to enter the picture. Okay. All right. So now let me write the lemma here. So the expected loss of be the perturbed leader is at most, well, I'll say, okay, is at most be the leader loss plus, okay, so now I'm going to say it's plus the max value, or actually I can just write it as the infinity norm of L0, and we can just take the expectation of that. So remember, L0 was this initial loss, and this is saying that the be the leader loss, the be the perturbed leader loss is at most be the leader loss plus the maximum loss that you added in the beginning. And this seems quite reasonable, right? Because this and so this is going to be should be fairly easy to argue. So the loss of be the perturbed leader. Okay, so now let's write this carefully. Is t going from 1 to t of LT of JT star. Right? This actually let me sort of rewrite this as opt plus that. Sorry for the messiness over here. Let me write this out separately. Opt plus the expectation of the infinity norm of L0, the maximum entry in L0. Okay, so now let's look at this as t is equal to 0 to t. LT of JT star minus L0 of J0 star. So what I've done here is I've simply added in, so when you're looking at the loss of be the perturbed leader, the actual loss, the time horizon starts from 1, not from 0. I'm just going to add in the fictitious loss at time 0 and subtract it out. So I'm just going to add in that fictitious loss and subtract it out. Okay? Now what's this? This is essentially the loss of be the leader on the loss functions L0, L1 up to LT. So this is the loss of B the leader if you also included that initial perturbation. And so by the lemma above, by the lemma of BTL, this is at most, this loss is at most the sum of t going from 0 to t of any expert of LT of IT star, which is the best expert in hindsight. So this is saying that if you look at any expert, and we'll specifically look at the best expert in hindsight, IT star, B the leader is going to be better than summation of LT IT capital T star, but the time horizon starts from 0 because you're including that fictitious, that initial perturbed loss function. So just to put it together, so I'll say this is loss of B the perturbed leader is at most the sum of t going from 0 to t of LT IT star minus L0 J0 star. And this, I can remove the first step out, so that's just going to be LT IT star plus L0 of IT star minus L0 of J0 star. So what is this first quantity? This is just opt. So I get opt plus L0 IT star minus L0 . Now these are just two random numbers. Two random numbers, right? Because the loss function was just generated randomly. So I'm just going to put 2 times that. Right? This is just saying that this is the maximum loss that you could incur, and I'm just going to crudely bound it as twice the maximum loss that I'm going to put in, the expected maximum loss that I put in. This is very crude bound, but I don't care. So this is saying that the loss of B the perturbed leader, which really makes sense, is just opt plus the maximum perturbation that you're going to add, which is kind of believable.
Wait, how did we get IT star?
I capital T star?
Yeah, I capital T star.
Okay, so here's B the perturbed leader, right? It's going from T1 to T.
Yeah.
Okay, so now I'm just going to add in what happens at step 0 and subtract out what happens at step 0.
Yeah.
Okay, so now let me focus on this. This is the loss of B the leader
Yeah.
if you include L0 as well.
Sure.
Because that's what JT star is defined to be, right? So for that sequence, for the sequence L0, L1, and so on, it's basically like IT star.
Yeah, but the best one in hindsight might not be.
You're right.
Oh, it's better than all of them, though.
Exactly, it's better than all of them.
Sure.
And therefore I can upper bound
Okay.
by this quantity. I can pick any expert that I want to put in over there.
Yeah. Yeah.
Okay, so far so good? So now we've done this step. So the loss of B the perturbed leader is opt plus this noise term. Now we have to figure out what this noise term is going to be. And we'll get to that, and we'll see that this is where the trade-offs of the noise are going to lie. So B the perturbed leader is essentially optimal plus the maximum perturbation that is added. Okay, any questions? Because now we're going to get to sort of the trickier, the real core of the analysis.
In the last equality that you showed where we included the opt, should that be greater than, less than or equal to, because didn't we show that the sum from t equals 1 to capital T of LT I star T is less than or equal to opt?
This is capital T star. This is capital T. So I actually plug in that specific expert.
Okay, got it. Never mind.
And I
Sorry.
simply chose the final best expert. So I just get opt.
All right, thank you.
Questions?
Here, preempts the bishop.
Okay. So if there are no more questions, sorry, I'm getting some feedback from someone, so I'm just going to mute.
Oh, sorry.
Everyone, no worries. Okay, all right. Okay, so this gives us be the perturbed leader. So now let's go to follow the perturbed leader versus be the perturbed leader. So follow the perturbed leader versus be the perturbed leader. So let's just recall. Let's go back to what these things are. So follow the perturbed leader plays J star of t minus 1, which remember is argmin of the sum of LT of S, and S is going from 0 all the way up to t minus 1. B, the perturbed leader, plays J star of t, and this is argmin of S going from 0 to t, so it gets to see the tth one. LS of I, so the only difference is here. And this is really where you start seeing the power of the perturbation. You say, look, this is just one more loss function than what happens here. On the other hand, L0 is going to be a, I'll say, somewhat large perturbation. So the addition of LT shouldn't affect the max, affect the min. That's what we're going to prove, but that's the intuition. It says if you're going to add this initial loss, which is this large random perturbation, then one additional function really shouldn't make a difference on what the min is. And therefore, FTPL is sort of very similar to BTPL. So it's really incredible when you step back and think of it. Like, each of the steps seems to make sense, but it's just magic. Because we know that follow the leader is bad, but be the leader is good. So if you can actually look at the current loss function and use that to optimize the past, then it's good. So that look ahead of 1 is extremely useful for the deterministic strategy. But when you have a randomized strategy, it seems like the look ahead of 1 really shouldn't help that much, because you initially add this large perturbation. So why should one extra function have much of an effect? And so therefore, it would say that follow the perturbed leader is similar to be the perturbed leader. But then be the perturbed leader is going to be similar to be the leader, which we know is optimal. Okay, so it's really magical. And the deterministic follow the leader versus be the leader are hugely different. But in the randomized setting, follow the perturbed leader and be the perturbed leader are not much different, which is remarkably saying that even if you got to see the future, it doesn't really help that much. Okay, so let's, before writing out some sort of formal theorem proof statement, let me kind of just walk through the argument at a more higher intuitive level, and then we'll sort of see what we're going to do. And we're going to set L0 to have like only negative entries. And this is just a convenience. It's just going to be convenient for us in the analysis to do so. So it's almost like initially we're going to give each expert, so negative entries, so this is like negative loss, which is really equivalent to a gain. So each expert will get an independent random gain from some distribution D. So I'm not going to tell you what that is, but that's what we'll see what the distribution is. It will actually derive what we want from the distribution. So each expert is going to get this gain in the beginning. So that's like some kind of budget for them to make mistakes. And if they make mistakes which are less than the gain, you just ignore it. So let me just sort of write this out in what's happening. And I'm going to refer, so this is L0, which was random. Right? And these are these random entries over here. And for convenience, I'm just going to denote these as x1 to xn. So x1, xi is the gain of the ith expert, which is randomly chosen. Okay. So let's look at, okay, so I'm going to sort of draw some stuff here, but let's first look at what is the loss of Follow-The-Perturbed-Leader. So this is the sum of t going from 1 to capital T, LT J T minus 1 star. Right? And we have loss of B the perturbed leader being t equal to 1 to t of LT of JT star. Okay, so now let me just subtract these, because what I want to do is I want to bound the difference. I'm going to bound the difference. So the difference, which is what I want to bound, is going to be LT JT minus 1 star minus LT JT star. Okay, so and then we could take the expected difference is really the expectation of all of this. Alright, so here's the key. And let me write this out as just linearity of expectation is the expectation of LT JT minus 1 star minus LT JT star. If JT minus 1 star is equal to JT star, then the term is 0. So if the expert did not change, then this is going to be 0. All the losses are at most 0, 1. They're within 0, 1. So I can upper bound this by saying this is the probability that JT minus 1 star is not equal to JT star. And this is the key. So the expected difference of Follow-The-Perturbed-Leader versus Be the perturbed leader is really saying that if you look at just vanilla Follow-The-Perturbed-Leader, how many times is it going to switch its choice? And essentially the number of times there is a switch is an upper bound on the difference. And we want to show that follow the perturbed leader is actually not going to switch its choices too many times. This is very interesting because let's go back. Let's go back to this bad example. What was the problem with follow the leader? Follow the leader kept switching. If follow the leader actually picked one of these experts and stuck to it for a while before deciding to switch, it would have actually performed quite well. I mean, depending on how long it decided to stay. But every switch was costing it. And what we're saying here is that there's a direct connection between the switching and the effect of the look ahead. The fact that B, the perturbed leader, gets to see this one extra. And this is the connection. So the expected difference between follow the perturbed leader and B, the perturbed leader, is the sum of probabilities of switching. Right? So at each step we say, what is the probability of switching? And that's what we get. Is this clear? This is a very important point.
Could you repeat how you get the intuition about switching from this?
So, what is the expected difference? It's just this quantity here, right? So I just do linearity of expectation. So I say that this is just the expected difference between LT of JT minus 1 star minus LT of JT star. Now look at this quantity here. If JT minus 1 star was equal to JT, then this term is 0. So if the experts were the same, meaning that if follow the perturbed leader predicted at time t what it predicted at time t minus 1, then there's no difference here. The difference only appears if there was a switch in the experts.
Oh, okay, I see. Oh, okay. Because we were one more time step.
Yeah.
Got it. Thank you.
Any questions? Okay. So what is the switching probability? So let's go back to what all of this really is. So let me look at another vector here, and I'm just going to look at. So I'm just let's think of these as vectors. Look at the sum of L S going from 1 to t minus 1. This is the sum of losses. Okay? And here is this other vector, which is just LT star. Okay, for convenience, I'm just going to name these as A1 to AN, capital A1 to capital AN. I'm going to call these little b1 to little bn. Then you have x1 to xn. So what is JT minus 1 star? JT minus 1 star says you add these vectors. So add the random vector to this vector, pick the minimum coordinate. In JT star, you add the perturbation to this vector to this. You add all three of them, take the minimum coordinate. So let me write this down. Sorry. Okay, so I'm just going to write this down here. So J t minus 1 star is simply the argument in this set AI plus XI. And JT star is equal to the argument of AI plus XI plus BI. Note that AI is going to be large. Potentially is, AI is because is the sum of the losses. But all the BIs are between 0 and 1. So does this make sense? Okay. So now let's sort of understand what this is. So let's just say that just to keep the indices a little cleaner, I'm going to say consider, you know, the leader, that is the best expert. So consider the leader JT minus 1 star being I. So let's say it's just I. Then what we have here is that AI plus xi. So for all j not equal to I, AI plus xi is at most aj plus xj. Or alternately, equivalently, xi is, let's just say maybe even strictly less than, is the min over all j not equal to I of aj minus ai plus xj. Right? Equivalently, we'll have it that way. Now, I think I should have, put a minus sign there. This is going to be useful for me, right? Because I said these were gains, so I'm subtracting this out. So equivalently, xi, moving this around, has to be greater than everything. So my apologies. So xi is going to be at least the max over all j not equal to I of ai minus aj plus xj. That's what it means for the leader to be I. So this is the condition for I to be equal to jt minus 1 star. Consider the leader j star t being I. Now what you need is for all j not equal to I, you have ai plus bi minus xi is less than aj plus bj minus xj. So you get essentially an equivalent condition. You get ai is greater than or equal to max of j not equal to I, ai minus aj plus bi minus bj plus xj. This is the condition for I being equal to jt star. Does this make sense? So to understand the leader switching, let's understand what is the probability that I is equal to jt star conditioned on I being equal to jt minus 1 star. Because what we can do is we can say the probability that jt star is equal to jt minus 1 star is I'm just going to sum over all I, and I write all these conditional probabilities down, times the probability that I is equal to j minus 1 star. So I'm going to analyze this. What is the probability that I will remain the leader conditioned on it being the leader at t minus 1. That means, what is the probability of this condition happening? I shouldn't say condition. This inequality happening, conditioned on this inequality happening. Okay? So just fix x2, fix all xj for j not equal to I. So just fix, you took some choice. Fix those choices. And call the max j minus I aj plus xj. Let's just refer to this as b.
Can you move it up? Oh, okay.
Capital B. Okay. So we know that xi being greater than b, this is equivalent to I being equal to jt minus 1 star. Now, if you look at this other quantity, this I can write as b plus little b, where little b is at most 1. It could even be smaller, it could even be negative, I don't care. And xi being greater than b plus little b is equivalent to I being equal to jt star. And what we're looking at, so just putting this together, writing this out carefully, the probability that I is equal to jt star conditioned on I being equal to jt minus 1 star, this is equal to the probability that xi is greater than b plus b conditioned on xi being greater than b. And this is what we need to bound. So we need to choose xi in such a way that this is easy to bound. And let's say, remember, b is going to be less than 1. B is going to be less than 1. And so what we'd like to do is give some lower bound on this. Because if we can lower bound this effectively, we will put that lower bound in over here. Thereby we will lower bound the probability that the expert did not switch. And if you can lower bound the expert not switching, so let me pull out.
Wait, what is E without a subscript?
Oh, it's just some quantity, right? I mean, I'm just saying that
Sure.
you're looking at this, so it's a maximum. So you're looking at a bunch of terms and looking at their maximum. And what you've done is you have added some small quantity to each of these and looking at the maximum.
Yeah.
So I'm just saying, whatever that maximum is, it's going to be at most this maximum plus something that is at most 1.
Sure.
Whatever that is, I'm calling that thing B.
Okay.
And I'm just saying that B is less than 1, because the BIs are going to be less than 1. These were the losses from the tth function.
Yeah.
Okay? And remember, now once I can bound this probability, I lower bound this probability, I will then upper bound this probability. And then I can upper bound the expected difference. This condition here suggests using a memoryless distribution, which is the geometric distribution. So suppose xi is drawn from a geometric distribution with some epsilon. So what does this mean? Remember, this is like you flip coins with probability heads probability epsilon until you get heads. So you keep flipping coins. Now remember, the probability that xi is greater than b plus 1 conditioned on xi being greater than b, this is at least 1 minus epsilon. or actually in this case it's probably exactly equal to 1 minus epsilon, right? Does this make sense? So this is really why the geometric distribution was chosen. And technically, okay, so I'll come to the technicality shortly, but do you see why you choose the geometric distribution here? So select xi from a geometric distribution with parameter epsilon. Then conditioned on xi being greater than b, xi being greater than b plus 1 is actually going to be 1 minus epsilon. And this holds for all b. So you don't even need to know what b is. This is the magic of this distribution. And so usually, I'll say technically, xi is drawn from an exponential distribution or a Laplace distribution which is some kind of continuous version of the geometric. I mean, the exponential distribution is a continuous version of the geometric distribution. The Laplace is kind of like, it has connections with the differences between these distributions. So a Laplace distribution is balanced. It's symmetric, that it can be both positive and negative. For the sake of our analysis, we don't need the noise to be both positive and negative. I just thought it's easier to look at a discrete loss. But in the analyses, you'll see that they'll draw it from an exponential distribution because the exponential distribution exactly has this property, which is the memorylessness. It does not depend on what b is, and you can bound this. And so you can then bound this by 1 minus epsilon. And so if you can bound the conditional probabilities by 1 minus epsilon, once the conditional probabilities have been bounded by 1 minus epsilon, now we can go ahead and we can write this out. We'll say this is at most the summation over I, probability that I is equal to j t minus 1 star times 1 minus epsilon, which is equal to 1 minus epsilon, because the sum of these probabilities is just 1. Because, someone has to be the leader. And so because this probability is 1 minus epsilon, now we go back here, and I'll say that the expected difference, so the loss of follow the perturbed leader minus loss of be the perturbed leader, this was at most the sum t going from 1 to t of the probability that jt minus 1 star is not equal to jt star, and this we see is at most epsilon times t. Okay, so we have to sort of
wait a second. We had this thing where we were multiplying the conditional expectation times the probability that is equal to I.
Yes.
What happened to the probability that is equal to I?
This is 1. This sum is 1.
Ah, okay, yeah, sure.
This is just saying that regardless of who the leader is, the probability of the leader switching is at most epsilon. And so therefore, the probability of the leader switching is at most epsilon, so we get epsilon times t.
Yeah.
So let's now chain everything together. Let's put everything together here. I'm going to have to show you. Okay, so putting everything together. So remember, we have the loss of BTPL is opt plus 2 times expected infinity norm of L0. Okay, so this is now where we're going to have some trade-off. So what we have is that the expected loss of follow the perturbed leader is at most the loss of be the perturbed leader. The loss of be the perturbed leader was opt plus 2 times this infinity norm. So let's go ahead and write that down. So it's opt plus, it's opt plus 2 times the expected infinity norm plus epsilon times t. So I'm just going to rewrite this as opt plus epsilon times t plus, and you actually don't even need the factor 2 because all the random variables are positive, but anyway, 2 times the expectation of the max over all I of xi, right? Because all these losses were basically like xi. So now it's just the max of this, where each xi was drawn from a geometric distribution with epsilon. So, okay, so let's look at this. What is the expected value of xi? What is the expected value of xi? You're flipping coins. Each coin is a probability of
epsilon.
1 over epsilon. So you know that this is going to be at least 1 over epsilon. Good. So you have this trade-off, epsilon versus 1 over epsilon. But you're generating n such random variables. How large can the maximum be? How large can the maximum be? Let me ask this again. How many times do you have to flip so that you're going to see a heads with probability at least 1 minus 1 over n? You keep flipping coins. How long before you're going to see a coin with probability 1 minus 1 over n? Remember, each coin is heads probability 1. How long do you need to go? Any thoughts? So this max, this expectation of the max, is essentially O of log n over epsilon. Now you can prove this in many ways. You can do it directly. You can think Chernoff bound. But think of it as, let's say, what is the probability that xi is going to be more than, let's say, 2 log n over epsilon. So this means that you need to see tails for the first 2 log n over epsilon rounds. So this probability is 1 minus epsilon to the 2 log n, so natural log over epsilon. And essentially this is like 1 over n squared. So now by union bound, you know that it's highly unlikely that any of the n random variables are going to be more than 2 log n over epsilon. You crank the math out, you can also get the expectation bound. So what you get over here is you get opt plus epsilon t plus O of log n over epsilon, which is exactly what you... I was not as careful as I could be, so I got t here and not opt. But you could be more careful, you get epsilon times opt. And so again, if you set epsilon to be root log n over t, then you get a bound of opt plus O of root t log n, which is the regret bound that we got earlier. And this is the trade-off here. So when you set epsilon to be large, when you set the larger you set epsilon, the smaller that this term becomes, but the larger that this term becomes. Now let's go back and look at this. When you set epsilon to be small, the random perturbations are large. So if you have large random perturbations, which means that epsilon is really small, then you know that follow the perturbed leader and be the perturbed leader are pretty much very similar. The more loss you add, more randomness you add in the beginning, the less effect that any individual loss function is going to have. So it makes sense that you want epsilon to be small, or you want the added losses to be large. On the other hand, if you put in too much noise, then B the perturbed leader is going to be very far from B the leader itself, right? Because there's too much noise, so B the perturbed leader is going to get confused by the noise, and that's given by the second term here, right? So this is the term that comes in because of follow the leader to be the perturbed leader. And this is the term that comes in between be the perturbed leader and be the leader. And the trade-off that you get is given by this epsilon. And it comes out beautifully that the right variable to choose is essentially a geometric distribution, or technically what you'll see in most of the in many of the papers is they choose it from an exponential distribution, which is a continuous variant of the geometric distribution. And so this is the analysis of Follow the Perturbed Leader. And I think one of the keys which I want you to take away if you go back and look at the analysis is really to try to understand why the geometric distribution is the convenient distribution to pick here. And it's because of this memorylessness. It allows you to analyze the probability of an expert switching in a sort of very convenient way. And what you get is another algorithm. We saw randomized weighted majority, and this gives another algorithm that gives a root t log n bound. And what is very nice is that it's actually very generalizable to lots of other settings other than experts, because this paradigm of follow the leader makes a lot of sense. And you look at your history, you optimize your history, and now what you do is you add some noise to it. And that's follow the perturbed leader, and then one gets provable bounds. So Kalai and Vempala showed its applications to many different settings. And since then, there has been a lot of work on such algorithms. This notion over here is also, it turns out, is close to differential privacy. So if any of you are familiar with differential privacy, you will know that the Laplace distribution plays an important role there. There's known as something, I think the first paper on differential privacy talked about the Laplace mechanism for differential privacy. The reason to use the Laplace distribution is, again, because you want a bound of this form. Like you want to have these sort of conditional bounds of that condition on xi being greater than b. What is it going to be? What is the probability that it's going to be greater than b plus little b? And you'd like to have some dependence only on little b, independent of capital B. Right? So the point over here is that this is independent of capital B. So this ends the discussion of Follow the Perturbed Leader. I'll end the lecture now. I'll take questions. And the next lecture, what I'm planning on doing is really to go back and talk a little bit about, can you do better than root t? And it turns out the answer is no, you cannot. And so what I'd like to show you is, give you at least one lecture with a flavor of how to prove lower bounds for randomized algorithms.